All right, so example 7. In this example, we're going to do the same thing as we did in example 6. We're going to find the absolute extrema. In this case, we're also given the graph to kind of give us an idea, a reference, a picture of, things the result that we got by doing the new system of finding absolute extrema. All right, so let's begin. We mentioned real quick that we need to find critical numbers and then test the critical numbers with along with the endpoints to the regional function to compare the y values. Remember that f of x is the y value. So here, real quick, these are the endpoints right there. So endpoints are x equals -8 and x equals 5. So what we need to define now is to find the critical number, critical numbers. Critical numbers. I'm just gonna say Cn, but that's what it means. So the critical numbers are found, as we mentioned before, whenever the derivative of the function is equal to 0 or the derivative is undefined. We already gonna see that in this case, either way, we have to find the derivative of the function. So let's find the derivative of the function. This is a simple, polynomial function. So we're gonna do the power rule along with the constant multiple rule. So for the first term, we have 2x cubed. The derivative of 2x cubed is going to be 2 times the power of 3, right? So it will be 2 times 3 is 6 times x raised to the power of 2, followed by the plus, and then same thing here, bring down the power down, multiply it by 9, that gives us 18 times x, and then subtract 1 from the power. That gives us 2 minus 1 is 1, but we're not going to write it down. And then minus 168 times x, which is just going to be 168. Remember, we just dropped the x value. And the derivative of plus 5, well, that's a constant term, which is a constant term. The derivative of constant term is 0, so we're not going to write it out. So there you go. We found the derivative. We can see that this is clearly a polynomial, so there's not going to be no critical numbers from using the derivative when the derivative is undefined. So because this is never going to be undefined, since this is a polynomial. So let's begin now. Let's find the critical numbers. We're gonna set this equal to 0, but the best way to do this is first by factoring as much as we can. So in this case, we're gonna factor the 6, and that's gonna leave us with the 3x here and minus 28, right? So we factor the 6 from the 6, factor the 6 from the 18, and factor the 6 from the 128. And then we're gonna come back and factor these out, and so we end up getting x x minus 4 times x plus 7, right? So x times x is x squared, and to get the -28, we have -4 times 7. So we're gonna apply this condition, right? So we're gonna put that constraint here, and we're gonna solve for x. So to solve for x, we're gonna use the zero factor property. That was the reason why we factored this out as much as like that. This implies that 6 is gonna equal 0, comma, x minus 4 equals 0, comma, x plus 7 equals 0, comma. But we already know that this is not a true statement, right? 6 cannot equal 0. All right, so we're gonna solve for the other ones by using basic algebra rules. So this will be x equals 4, and this will be x equals 7. All right, so what we're going to do now is we have found the critical numbers. So let's make sure we box this, because those are kind of a big deal. All right, so we found those two. What we're going to do now is we don't have to test whether these are local max or local min. All we got to do is plug it into the regional function and compare the y values, right? So we're going to compare the endpoints. So the endpoints are -8 and 5. And then we're going to do the same thing for the critical numbers. We have f of 4 and f of 7. So let's take the original function. Let's write it up here, and we're gonna have 2 times x cubed. I said x cubed, but I wrote square, plus 9x squared minus 168x plus 5. So what we're gonna do is for every single one, we're gonna replace x with negative 8. Do the same thing for the next one. Now replace it with 5. And you guys can see that we're going to put this in the calculator. Now plug in 4. So you can use the calculator to put these numbers. Alright, so if we put this in the calculator, what we're going to end up getting for the first one is going to be 901. For the second one is going to be, is that supposed to be a negative right here? Yeah, negative, 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 right? I missed the negative there. So that should be a negative. So that would be for 5 would be negative 60. For 4 would be negative 395. And for negative 7, this would be 936. Okay. All right. So comparing these numbers, by comparing these numbers, remember that we plugged this in the function, right? In the original function. So this is the y values. So the y values in the function, the highest one you can see here is this one here, right? This is the highest value. So this is the absolute max. And then the lowest value of this is going to be negative 395. This one. So this is absolute min, right? Minimum. So there you go, right? We found this value, so we're gonna write them over here. 936 is the actual maximum value, the value of the function, and it happened in x equals negative 7, right? So the minimum value is negative 395. And it happened at x equals 4, right? I don't have to write the x here because it's already there. So there you go, right? So if you go back to the graph, just to kind of give us a perspective, at negative 7, you have the highest value of the function, right? And at 4, we have the lowest value of the function, right? And in fact, it was, what, roughly around 395, and this is roughly around 936, right? So I hope that you guys found this helpful. I think this is a pretty nice approach, right? Just a quick recap: find the critical numbers and test them along with the endpoints into the regional function, right? You don't have to actually find the local max, local min. All right, so let me know if you have